The normative 4045 is about magnetic materials and specifically about permanent magnets that are magnetically hard materials and the methods of measurement of their magnetic properties. The physical observables involved are the magnetic flux density B, measured in Tesla, the magnetic polarization J, also measured in Tesla, and the magnetic field strength H in ampere/meter, that are related each other by this formula, where the magnetic constant μ0 is expressed by this number, that is not anymore 4 pi 10 to the minus 7, as a consequence of the revised international system of units. In particular, in the new definition of the ampere unit, the magnetic constant is not defined a priori, but is a measurable quantity. For more details about this, you can see this work on IEEE magnetic letters. In the framework of this physical observable, we want to measure the demagnetization curve and the recoil line within the method that will be shown in this presentation. By taking into account a given hard magnetic material, we can measure two hysteresis loops, as it's shown in this figure. One is the magnetic flux density B as a function of the magnetic field strength H, and the other is the magnetic polarization J as a function of the magnetic field strength. Both the loops have a value of coercivity, that is the magnetic field strength, that has to be applied in the second quadrant in order to achieve B or J equal to 0. These loops have to be measured in a closed magnetic circuit. Another subject obtained by the measurement of the hysteresis loop is the point at which the modulus of the product B times H has maximum value, as shown in this example, where the working point is I line over the demagnetization curve. The measurement conditions are the following. The magnetic field strength is applied by means of an electromagnet. The sample and the poles of the electromagnet have to be symmetric. The magnetic flux density is measured by a coil and the magnetic field strength is measured by a sensor, such as an Hall probe. In the figure you can see a schematic representation of the measurement setup. In these pictures is shown an example of an experimental setup, with the electromagnet and the sample between the poles. In the zoom picture you can see the sample with a 10-turn coil for the magnetic flux density measurement, and the Hall probe for the magnetic field strength measurement. The uniformity of the magnetizing field is guaranteed when the following geometric conditions are met. D2 represents the diameter of the cylinder where the field is uniform. D1 is the diameter of the pole. L is the distance between the poles that corresponds to the length of the sample. The poles of the electromagnet have to be designed according to the following criteria. The saturation magnetic polarization of the poles material has to be far from the values of flux density used during the measurements. The sample and the poles must have the same axis. The demagnetization curve, that is the second quadrant of the hysteresis loop, shown in the red square, is determined after bringing the sample at maximum magnetizing field. The criteria to determine the value of this maximum magnetizing field is the determination of the magnetic saturation of the sample. The definition of magnetic saturation is formulated by these conditions. Now we focus on the sample. It has to have a simple shape, it has to be symmetric in order to avoid an air gap contribution, and it has to be uniform in its dimensions. When it has a cubic shape, it is necessary to mark on the sample the direction of the magnetizing field, as shown. The measurement of the magnetic flux density is performed by integrating the voltage at the search coil around the sample. It is necessary to take into account the number of turns n, the cross-section of the sample A. The wires that are connecting the coil have to be tightly twisted in order to cancel out some possible extra voltages due to the magnetic flux detected outside the sample. Another spurious source of signal is due to the flux in air that can be cancelled by taking into account the cross-section of the search coil together with the cross-section of the sample. The most efficient way to compensate the magnetic flux in air is the use of a two-search coil device. This device is designed so that the coils are electrically in opposition and the product number of turns times the cross-section is the same for both the coils. This is a picture of a real two-search coil device, and we can see that it allows the characterization of a sample whose geometry is not compatible with a single search coil. The measurement of the magnetic field strength relies on the continuity of the parallel component of the vector at the interface. This allows to place a sensor near to the sample with some geometrical criteria. The sensor can be a flat search coil, a magnetic potentiometer, and Hall probe. The demagnetization curve has to be measured in a controlled temperature, and the variation of the magnetic field strength has to be sufficiently slow to avoid phase difference between H and B, or eddy current in the sample. The information obtained from the measurement of the demagnetization curve are the remanence, the working point, and the coercivity. The recoil line and the recoil permeability are the slope of the variation of the magnetic flux density over the variation of the magnetic field strength obtained by increasing the magnetic field strength from coercivity. To conclude, according to this normative, it is necessary to provide the information listed on the left column in order to characterize an arc magnetic material in terms of remanence, working point, and coercivity.